and because definitely this is not as the workload is not similar to project 1, it is slightly higher, or actually more higher, and so maybe you want to take a look at it weekly so that we get a lot of time to work on this. And worksheets 1 and 2 are graded. I have it with them. I can keep it somewhere here, and you may take it during the break. And worksheet 1 is graded for 35 points total, and worksheet 2 is graded for 48 points total. But all the worksheets will be weighed equally at the end. Okay, even though the points may differ for each worksheet, they will be weighed equally. Do you guys have any other questions or any concerns? Okay, so if there are no other questions, I think let's get started. So first I'm just going to do a high level overview of what we have completed till now and what we are going to start from today. So we started our course in virtualization. We were interested in seeing how the CPU is being virtualized, how the operating system virtualizes the CPU, and one more main thing is how the operating system virtualizes the memory. These are the two main resources that we have on the computer that is made use. The programs that are running on the computer are making use of CPU and the memory, and the operating system virtualizes these two resources for the programs. And we already completed CPU virtualization, and if you remember, we saw in CPU virtualization saw two things the mechanisms, that's the first thing that we saw, and then the policies. Usually mechanisms are more harder because there we talk about how exactly it is happening internally, in the sense what is the hardware support that we get, or how does the operating system really tries to virtualize the CPU. In that the mechanisms that we saw, where one of the mechanisms was the limited direct execution, and the other mechanism was context switching. Okay, we saw all those things in the mechanisms, and we also saw policies, and we saw a bunch of scheduling policies first come first serve. Then we saw the shortest job first, shortest time to completion first, and round robin. Those are some basic policies. And then we also saw in the real world scheduler policy something like the multi-level feedback queue, which you are going to implement for your project too. And after that, we also saw how to create processes, how to create new processes from a user level program, and how do we really make that process to do some specific task using the exec VP that we saw. Okay, so with respect to CPU virtualization, what was the main abstraction? What was the main abstraction that the operating system had about each and every running program? Pardon? Yeah, so they think they each have their own CPU, but what is that they process exactly? So yeah, so we have the important abstraction that we have is the process here. Okay, so in a similar way, now from today's class we are going to start memory virtualization, start learning how does the operating system virtualize memory, and here again the structure is going to be very similar. We are going to introduce the abstraction. The important abstraction with respect to memory virtualization is nothing but address spaces. We are going to talk about this in detail, and then in a similar way we have mechanisms for memory virtualization and even policies. And here the mechanisms are we'll start from very basic mechanisms how it was a few years back and how it was this. some years back, and then like we'll just come and see like the mechanisms for memory virtualization that are implemented currently, okay? And that is going to be our idea here. And so we are going to study the mechanisms for memory virtualization in a lot of detail, and so we'll be like covering mostly using this whole class, and even the next class completely just for the mechanisms for memory virtualization. Okay, and the policies are like pretty straightforward. Again, it will be very simple, very easy, as we saw like the policies in CPU virtualization. So here, in memory virtualization, okay, let's start with the important abstraction that we have here, which is called the address space. Okay. Okay. So an address space is just a list of addresses that a particular process can access while it is running. Okay. So the operating system creates this abstraction of an address space for each and every running process. So let's assume if there is a process P1, when this process is being executed, it can access a list of addresses. Operating system use the list. Let's say starts from 0 and it, let's say, goes to like n minus 1. This is n minus 1 address. Okay, this is the 0th address, and the operating system can only access this set of addresses 0 to n minus 1, and this particular set of addresses is usually divided into like segments like code, static data, heap, and stack. Okay. And usually the heap grows like upwards and the stack grows downwards, and these are like the lower addresses are here and the higher addresses are here. This is how it's usually done. So now what we'll do is, so this address space is for each and every process. By that we mean each and every process has its own address space of code, static data, then we have the heap, and then we have the stack. Okay. For the purposes of our discussion, from now on, maybe like we will just consider these two segments. Okay. These two sections, the code and the static data, together as just the code. Because code and instructions, we can just say them is just the code. Okay. So for our discussions hereafter, we are just going to have the code segment, which contains, we may assume that it contains both the code in the program and the static data. Then we are going to have the heap, and then we just have the stack. Okay. So the three segments that we have are in a particular address space. So in the old days, when people were like running programs, it would be more like, let's assume if this is our physical memory, and let's assume physical memory starts at 0. For simplicity, let's assume our physical memory is of maximum size 64K. It's like unrealistically small, but for the purposes of the discussion, this should be fine. Okay, it's just we have a memory of size 64 KB. Okay, so the maximum address, since it starts at 0, this address here is going to be 64K minus 1. Okay, that is the maximum address there that we have in the physical memory. So now, when a process is running, let's assume that's a process P1. It has its address space. This entire thing is the address space of P1. Okay. It has its code. It has its. We just told we are going to consider these three things: heap and stack. And if you want to like run this particular program, okay, this address space, okay, or whatever, wherever the code, heap and stack, these things need to be loaded in the computer's main memory, the physical memory. And only then you'll be able to actually execute that particular program. Okay? So here we may assume that we start at 0 and each process has an address space of 16K. Again, unrealistically small, but it's fine. Okay? So the maximum address that a single process can access is 16K minus 1. Okay? That is the maximum address that a single process can access. So since we have 64K, let's just like first divide this whole memory into like 4 regions, okay, of size 16K each. So, and in this class, just making a few assumptions, the K that we are talking about, okay, the kilo that we are talking about is just 2 to the power of 10. Okay, and whenever we say M, there are like a lot of minute details like kilobytes and K. There will be like small subscript called I. Ki is the actual 2 to the power of 10, but for the purposes of this class, we may assume this K stands for 2 to the power of 10. Mega stands for 2 to the power of 20, and the giga stands for 2 to the power of 30. Okay, these are assumptions. And we will be using this a lot in memory virtualization. Okay? And so we have this setup currently. Usually, in the physical memory, the initial few addresses, for example, in this case, the first 16K addresses, usually occupied by the operating system. The operating system uses it for its own purposes. It will have its code, its data, its like stack and heap here. The scheduler, for example, when it is running, the program, actually the code for the scheduler will be somewhere here in addresses somewhere between 0 to 16K. Okay? Then now if we want to like load this particular program P1 into this thing, we can load it like either we have like 3 slots here, okay? So we can just, let's assume we load it like here. We load it here, it's just like P1's code is going to be here. And then P1's, while the program is running, P1's heap is going to be here, P1's stack is going to be here. We are like, this is not exactly correct because if you think about it, we are talking about a lot of details here. When I just told, okay, this is the address space of a particular process, okay? So when it is actually on the disk, we are not going to have the heap and the stack. As we already discussed, we are not going to have the heap and the stack when you have, when a program is stored on the disk. It is only going to have the code and the static data. But when you are loading it into memory, and when your program is executing, it's going to have the code, then the heap, and then the stack, everything. Okay? So whenever we talk about an address space, we are assuming that this thing is in the physical memory. Okay? Whenever we are talking about an address space, we assume that this is the set of addresses that a particular process can access in the physical memory when it is actually executing. Okay? And so in this setup, we have P1 running here, and if there is one more process, let's say P2, same 16K addresses, then you may load P2 somewhere here. P2 can be loaded here. So P2's code will be here, P2's stack, heap and stack will be somewhere here. So we are making a lot of assumptions here, okay? First assumption that we are making here is, okay, the assumptions that we are making here in this case. The first assumption is the process address space, the process's address space is contiguous in physical memory. Should be by that we mean, so this was like a setup that was like in the older systems, in the very old systems, this was how programs are really running. When you want to like really run a program, you need to have, let's say for example, if you want to run P1, you need to have 16 kilobytes of contiguous storage for running P1. So only if there are at least 16 bytes of contiguous storage somewhere, in your physical memory, the operating system will be able to load that particular program in the memory and start executing it. Okay? So this is the first assumption that we are making. And the second assumption that we are making is the address space of a particular process. Okay? The address space of a process will be always less than the physical memory. So in this case, it is nothing but we are just assuming that address space of a process is only 16 KB, but the physical memory is 64 KB. And so address space of processes are less than physical memory, but in reality, these things need not be true. Okay, we will be looking at those things in a little more time, but these are the simplistic assumptions that we are making so that we can start learning like how memory virtualization really works. Okay, the third assumption that we are making is all processes have the same size of address space, or the address space of all the processes is the same. Okay, the address space of all the processes is the same. So in this case, we are just assuming all the processes in our system is going to only have 16K of address space. It cannot grow more than that. It is the maximum that it can have. You cannot even have like processes that are like that has only 8K of address space or something. We're just assuming these things. And so in this setup, the maximum number of processes that we can run at a single time is only 3. Because operating system is already occupying a spot. Other than that, the maximum that you can run at any point in time in this particular setup is only 3 processes. Because you only have 3 contiguous regions of 16 KB that are there. Just think what may happen if we had loaded the process P1, okay? If we had loaded in this particular setup, if we had loaded the process P1 by mistake, if we had loaded it at, let's say, starting at address 30K, if we had loaded the process P1 starting from here, okay? Starting from here, like 30K. Then how many processes we may be able to run at the same time? Just 2 processes because the bottom part is like not usable, but we can like load one more process in the top. So let's just like have this here. Now what we may do is so we're just going to create a memory file and try to like print out some addresses, okay, from our particular process, just to make sure if the assumptions that we have here are actually true in a real running process, okay. So the first thing that we're going to print is like, let's just try printing the address of main, okay? So the address of main is going to give us the start of our code section basically. Main is just the code, so that particular function will have an address internally. And if you try to print out the address of main, and if you want to like print out the address of the key, what can we do here? Just malloc 1 byte or something and just print out that particular address. And if you want to just print the address of a stack, you have to do is variable here. And then just print its address. Okay, just create a stack variable. Just print its address. I think we need to include standard lib for malloc. So can you see like the main? Okay, the main starts at some address. Main is currently at an address called 4 in hexadecimal 400578. Okay, and then the heap is starting at a higher address than the main. So we can now compare this with our view of the address space. The code starts at the bottommost part, and then we have like the heap somewhere there. And if you see the address on the stack, it is like so high because it is on the other end of the address space basically. So this shows that the assumptions that we have currently about how an address space is organized is actually true. Okay, and yeah, so why is main not loaded from address 0? Exactly, so in each and every address space, even though in diagrammatically we show that, okay, we have the code from the beginning, okay, internally the address 0 for a particular program, okay, will be like reserved by the operating system. Not only that address 0, a bunch of lower addresses will be reserved by the operating systems, and it will not allow the user program to access it. And so the code only starts from here. Okay. So now a question. So if we, let's say, if we go to this particular, if we are able to find the contents, okay, of this particular address 20EA010. Will we be able to, and assume we malloc like a single byte, right? We malloc a single byte, and if we go to this particular address in the physical memory, will we be able to see the contents inside that particular byte? No? How many of you say no? Great. How many of you say yes? Okay, so great. So we will not be able to like find the contents there because why? These are just like virtual addresses. Okay, what do we mean by virtual addresses here? Is like the program has a view of its address space. It thinks that it has some addresses starting from 0 till like n-1, which is this. You may assume that this is the largest address or something like that. Okay, and even though the program thinks it that way, the actual place in the physical memory where, let's assume, our code, which is the main, or our heap or the stack is actually placed is totally different, which the program has no idea about. The program has no idea where they are actually placed in the physical memory. And how does that work? So the program has this view, like very simplistic view of saying like, okay, it can access addresses from 0 till like n-1. But let's assume if we talk about an address x, okay? If we talk about this address x, this address is not the actual physical address x that is here. So in the physical memory, this entire physical memory, this x may be somewhere here. Let's assume, so now let's assume if this is like hexadecimal like 1000. In the physical memory, if this is 100, the contents of this particular memory location for this particular process may not be right here. The operating system will make sure that it is placed somewhere else, okay? And it actually, so for example, it may be placed, let's say if this process was loaded somewhere here, if this process was just loaded somewhere here, then this address will fall. So if this is P1, then this address will just fall somewhere here. So now this address may be let's say 3000, something like this. So the user program, whatever the user program thinks to be an address like 1000 in hexadecimal is internally in the physical memory. It may be placed completely like at a different location. Because physical memory, so starts at 0 and it has like some 1 and it is right here, right? And so in this process of like placing the address space of each and every process at completely random locations in the physical memory, it's called like memory virtualization.
Is it possible for it to randomly be placed at like the same place it's virtualizing, and they always make sure that's not the case for security?
Yeah, so these are like very basic systems that we are discussing. We will go and see like how it is actually. So it will not be, we will have no idea like where exactly it's going to place. So definitely for security, if we know like where it is going to place the first process or something, then the users may easily attack the system. Yeah, so we have no idea where it is going to be placed.
Can you say again why the process didn't start at 0? Did you say the OS was using the addresses lower than that, or it was just randomized for security?
So it is not randomized for security. It is like the OS for in Linux. Okay, in Linux, the OS just starts the code section at some point higher, like in the virtual address space. In the virtual address space, if you try to access the virtual address 0, that is what is called a segmentation fault, or like accessing a null pointer, right?
But why?
So we want like a way. So one of the reasons is we want a way for the user program to access to some memory location that is not existent. And so the OS reserves the memory location 0 for that particular purposes. And even if you remember, like the OS has its, other than that, each address space of a process has two parts, right? The user part and the kernel part. The actual kernel part will be in the lower addresses, in the virtual space. You remember? Each address space has two parts. The actual kernel part for each and every process will actually be in the lower addresses. So basically the OS has its code, data, and we have the kernel stack. Even the kernel stack will be there in the lower addresses. And the addresses that we just saw here, when we ran the program, were just the user space addresses of user space virtual addresses, basically. Make sense? Okay.
Just to clarify, so the kernel portion of process 1 and the user portion of process 1 share a address space?
The kernel share the same address space, yeah. So the user portion of process 1 and the kernel portion of process 1 share the same address space. But now, till now, when we were discussing, I was only thinking about the user portion of the address space. I was not even thinking about the kernel portion. So the addresses that you saw, like let's say main started at some 0x4000 something, right? All the addresses that are below that were reserved for the operating system, even in the virtual address space of a particular process. So if we like redraw this virtual address space diagram, just saying like this part was just the user part that we're talking about here. We all like below here we even have the kernel part. Okay, and usually like the parts, so we always in the physical memory. Okay. And here, whatever we are drawing as the OS is the actual space in the physical memory that the operating system is taking up. Okay, so the code, the data of the operating system needs some space in the physical memory, right? It does not spread its use in the physical memory to multiple locations, but it just uses a specific part. Usually, it will be like around like 4 MB or something like that it occupies in the RAM. Okay, the initial part of the RAM will be occupied with the operating system.
Is that what we initialized when we boot up? That we were figuring out where we're going to put the OS?
Exactly, yeah. So those things are taken care of when we boot up. Yeah. So now, okay, this process of just like placing the addresses of or the program, the data stack and heap of a particular program, of a particular process at random locations, which the process doesn't really know, is actually virtualizing memory. But why do we even need to, why do you think the operating system virtualizes the memory?
So that it can utilize more of the memory by splitting it up into places.
Yeah, so that is we'll be learning that after some time we can actually split up a particular address space into multiple smaller chunks, and then we can utilize most of the physical memory that is available. But in this particular setup, so in the setup where we are not able to split up a particular address space, a program has to be loaded contiguously in the physical memory. Why do you think virtualization is needed here? Exactly. So to keep one of the reasons is to keep the memory in a secure way, to maintain the memory in a secure way. So for example, if you don't have this virtualization of memory, and if the process or if the user of this particular process may decide where to load this particular program in the physical memory and execute it, let's assume by mistake if the user says, I want to load the program at address 0 in the physical memory, P1. P1 will immediately, the operating system will be immediately overwritten by P1, okay, and then your system will crash. It will become unusable, okay, and so the operating system keeps, protects its code, data, stack and heap. Operating system protects its address space from other programs using memory virtualization. And any other uses memory virtualization. So one more important use of memory virtualization is just to protect the processes from each other. If there are two processes that are running, let's assume P1 is running here and if P2 is running here, just in case if there was no memory virtualization, then P2 would be able to go and access some contents in P1. Or P2, if you give the control to P2's user to load wherever he or she wants, then P2 may be loaded here, where P1 was executing. Again, you are interfering with other processes. But in this case, since we have memory virtualization, what is happening is P2 has no idea where it is going to be loaded in the physical memory. All it is trying to do is just say, I have some data here, okay? Using variables, let's assume I have a variable here, I have another variable here, y. I just want to add these two things and put it here, in this particular z. So these addresses of x, y and z would in turn just be virtual addresses, but internally in the physical memory, the places where this x, y and z will be placed will be totally will be transparent to this particular program. So here, what we mean by transparent is the program really has no idea where its address space is being placed, okay, or where is it currently executing in the physical memory. Only the operating system takes care of it, okay. And one more reason why virtualizing memory is important is if the operating system does not virtualize memory, then it is the programmer's responsibility to say, okay, I'm creating this particular data structure. Can you please place this in this particular memory location? And then I want to place the next data structure in this particular memory location. It will be so messy, think about it. There will be a lot of responsibility for the programmer, but in this case, the programmer just needs to think at a higher level, in terms of variables and stuff like that. Really, the programmer need not worry about the actual memory allocations internally. Now let's take a very simple example. Let's assume a function like foo as variable x. It's 100. And then we just say x equals so void function. Okay. We have this simple function, and if in assembly this function maybe, let's assume we have the instructions like move. Let's assume x is at some address like 1004. Okay, move the contents of this memory location to the register EAX. Then add value of this is 10, add value of 10 to the contents of EAX, and then store the contents of EAX back to the memory location. These are three instructions that we have here, and let us assume, okay, these three instructions are at addresses, let's say 128. Okay. These are the virtual addresses in which these three instructions are present. And the reason why this thing has just like 4, okay, this address occupies 4 bytes in memory, and that's why the next instruction starts at 132, but this instruction just occupies 3 bytes in memory. Because in x86, the instructions are actually variable sized. Okay? And this may again occupy 4 bytes of memory. Now we have this setup. Now, when we are trying to, now the intention is to run the instruction at virtual address 128, okay? When the CPU is trying to execute this instruction at 128, how many memory references happen? Just think about it for like a few seconds. The question is how many memory references by here, okay, by the memory reference here we mean actually accessing the physical memory, okay? How many total memory references happens for executing this first instruction? Yeah. How many of you say it's like one memory access, 2, 3? Okay. So why do you, let's say like, why do you think it's 2? Can someone say, reason out why?
One, to read in the opcode to figure out how many additional bytes of data need to be read from memory for the rest of the
So basically
instruction.
reading that particular instruction, yeah. And one more for?
Well, so one to read just like the opcode, and then that from the opcode you can determine how many additional bytes you need for the arguments, or kind of like in this case the address and the register that were.
Yeah, so in that case it is one instruction, right? One memory access, right?
I thought like the first byte or 2 is the opcode.
Oh, okay. So you may assume that when we go to, let's say, if you're going to the actual location of 128, wherever this particular instruction is stored, you will take the entire 4 bytes and come. You can assume that accessing those 4 bytes to be a single memory access.
Okay.
So we're reading line 128, and then we have to read line 0x1004, so that's 2.
Exactly, yeah. So the 2 accesses here are reading. We need to like once read the particular instruction from memory, the code itself, this line of code, move this particular thing, this is residing in memory. So one access is for just reading this particular instruction, and the second access is this instruction in turn has a memory reference. It says, go and take the contents of the memory location 1004 in hex, okay, and then place that particular contents in a register. So this single instruction has like 2 memory references.
Isn't there more of that because it has to find out where it's mapped to the actual memory?
Yeah, so that is like, we'll look at that like more than that, but yeah, for in this simple case, you can assume that it's just 2, yeah, okay? But actually it's more, okay? More than that, we will, by the end of this class, we'll understand that it's not just 2, okay? But as of now, we can assume that it's just like 2 memory accesses for this first instruction. For the second one, exactly, just 1, because for the second one, only memory access is just to load that particular instruction from memory, and within that instruction, we really don't do any memory manipulations. All we do is just add a value of 10 to the contents of the register EAX, okay? And the third one again has 2 memory accesses, one for fetching the memory and one for actually fetching the content, like storing the contents of EAX inside this memory location. So now, let's assume a few things here. So in the virtual address space, if this is our code, okay, let's assume 128 is here, 132 is here, and 135 is here. Okay, the 3 instructions that we just wrote here are actually here in the code segment. And if in the physical memory, if we load this particular process, let's say this is P, we load this particular process at 32K, load it to 32K or 32KB, and the process resides here. Okay. So can you figure out what are the actual physical addresses that are going to be accessed? We just saw like there are like 2 for the first instruction, then 1 memory access for the second instruction, and 2 memory accesses for the third instruction, right? Can you figure out what are those actual physical memories? Like what is the byte number in physical memory for these 5 memory accesses? This is the setup that is given. So again, the code is here, the heap is here, and stack is here. So it is more like this. If this is the virtual address and if this is the physical address, we have the virtual address like 128. Then the second virtual address that is being accessed is. So for simplicity, okay, let's just change this. Instead of thinking that it is at somewhere here, let's just assume it is at address 200. Okay, even here, let's assume that it's just at address 200. Okay, this is the setup here. Then what are the physical? So second virtual address that is going to be accessed is 200, the third virtual address is 132, fourth virtual address is 135, and fifth virtual address is again 200. So in physical memory, what are these just going to be mapped to? If you just think about it, here we are assuming since you're starting at 0, okay, the 0 just maps to 32K. Because it is placed right there. And so 128 is just 128 bytes away from 0. And so all you have to find out is just say 32K plus 128. And this would be the actual physical address for the first memory access. In a similar way, you can easily figure out this is going to be like 32K plus 200. Actually, this may be wrong because this should be like a large address. If you think about it, this address should be like a large address basically because it is in the heap segment, right? Just for correctness, I'm saying like this X is in the heap segment, so it should be like a really large address, and so this should be something like, sorry, in the stack segment, sorry, it is in the stack here. It's a local variable within the function, it's in the stack, so it should be like really high. Okay? And similarly, you can just figure out like, okay, these things are 32K plus 132, 32K plus 135, and 32K plus 20,000, something like this. Okay? And this type of relocation, okay, for doing this type of relocation, the operating system again needs some support from the hardware. Okay? It can't do it by itself, because if you think about it, what do you think is the hardware support that we need here? So for example, for context switching, one of the hardware support that we needed was, what did the hardware help with context switching?
Kernel,
Pardon?
the mode.
The modes, the kernel mode and the user mode, and one more thing, definitely that it added a bit of like, if it is in the kernel mode or in the user mode, there was one more thing for context switching.
Save the stack, I forget which one.
No. Exactly, the timer interrupt, right? The timer interrupt was some support from the hardware, without which we couldn't have a preempted currently running process. In a similar way, can you think about what may be the hardware support that we may need here to make this type of relocation work? This particular thing is just called a relocation. We are relocating a particular piece of, let's say the code, the program thinks it is at 0, but it's actually relocated in the physical memory to the address 32K, right? So for this type of relocation, what do you think should the hardware support?
Should support translation to cipher, just a way for it to look up memory addresses without trapping in the OS every time. Sort of
So that is definitely one of the support that it provides, but for this simple thing, I don't think we need a TLB access, but we'll be looking at that in the next class, okay? So for this simple thing, if you think about it, okay, one more easy way to think about it is like, if this is like process P1, then P1 is loaded here, okay? If this is P2, P2 is loaded here, and if this is P3, P3 is loaded here. So the operating systems need some way to find out, okay, if they are talking about P1, P1's code starts at 32K. If the current running process is P2, then P2's code starts at 48K. If the currently running process is P3, then P3's code starts at 16K. You understand? The operating system needs to figure this out, the base of the address space, where is the address space loaded. And so, for this particular thing, the hardware has a, like a system, okay. Again, if this is the hardware that we're talking about, it has a particular, like a sub-unit inside it. It's called the memory management unit, okay. And this memory management unit just provides 2 extra registers. Okay, the 2 registers are, this is the first register is called the base register, and the second register is called the bounce register. Okay, so in this case, if let's assume if P1 is currently running, P1 is running on the CPU, the base register's value for our simple example here is going to be 32K, okay? And the bounce register's value is going to be 16K, okay? In this simple setup that we have, since we are assuming that each and every process is going to be of the same size, okay? The address space of each and every process is just going to be 16 KB always. The bounce register is always going to be 16 KB in this particular setup, okay? But can you think like, why do we need this bounce register? Just think about the base is to find out where does the address space start. But why do we need a bounce register? Exactly. If some process, let's say when P1 is running, if it says I want to access the virtual address 17K, okay? If the operating system doesn't really care about how much P1 can access, then 17K from here, starting from here, 16K ends here, 17K is going to like shoot up somewhere here in process P2, which is bad, right? So P1 at this time is able to access the memory of process P2. So the operating system should not allow this, and for that, operating system has a bounce register. So whenever a virtual address is given to the operating system, even before it tries to translate it, all it does is just check the address with the bounce register. If the address is greater than the bounce register, immediately it throws the operating system throws a segmentation fault. Okay, and the process is killed. If the address is within the bounds, less than or equal to, actually it should be less than, strictly less than, it should not be equal to because the maximum address a single process can access is 16K minus 1. Is that right? So it should be less than. If the address that a process is accessing, let's say if it is less than 16K, then what the operating system will do is, now the hardware has provided us this particular support of the base and the bounce register. It first checks with the bounce register. Let's assume the virtual address that this particular process P1 is trying to access is address 1024. Okay. It just first step is just takes this 1024 and checks with this. This is the first step that happens. Okay. The first step is just saying is 1024 less than 16K. Okay. Yes. Once it's done, then what it's going to do is just take the base value directly from the base register for this particular process and just say I'm going to take the base register's value, add it with the particular whatever physical address that I got, 1024, and this just gives me the physical address. Okay? So does this make sense? So here it's like very simple. If you want to like get a physical address, all you are doing is just get the base register for that particular process, add it with that whatever address that you're trying to access, the virtual address, okay? Then you get the actual physical address. And this type of relocation, this simple type of relocation is actually called base and bounds relocation. Other names for this is dynamic relocation or hardware-based relocation. These are three different names that this particular mechanism has. This is the first mechanism that we just saw about how do we translate a virtual address to a physical address, and the process that we just saw of translating a virtual address to a physical address is just called address translation.
Is that where the hard limit for the number of processes you can have comes from?
Pardon?
Is that where the hard limit for number of processes that an operating code, the number of processes you can run, like we talked about 64 in last class?
Yeah.
Is it always tied to the hardware?
No, that's a very good question. Okay, so in this case, if you're saying like there is one base register and one bounce register, then let's assume if a different process is going to run, then what do you think should happen? What is the responsibility of the hardware here? Let's assume the operating system chose process P2 to execute on the CPU currently. The operating system, the hardware and the operating system together, when they are doing the context switch, okay, now they just need to make sure that the correct value of the base register and the bounce register for the second process, let's say P2, should be loaded in these registers. Because these are just a single set of registers. The base and the bounce are just like a single set of registers. Even if you can run, let's say, 64 processes on this machine, and all the 64 processes are just going to share these single set of registers.
Was that the hardware step when we were talking about context switching a couple weeks ago? Or the hardware step where it said it would save the kernel stack registers?
So the hardware saves the user mode registers to the kernel stack.
Okay. But that's not concept.
So the hardware actually saves the user mode registers to the kernel stack, and it also like takes care of saving these things. In the context switch, now it is an additional responsibility for the hardware and operating system to make sure that these values are saved. Okay, but where will they save it? Where will they be saved? Exactly. So we just need to add two more fields in the process control block PCB, saying like this is the base for this particular process and this is the bounds for this particular process. So whenever it is not running, it will be saved there. And so whenever it is going to run, you just load it from the PCB and store it in these particular registers. Does this make sense? Because based on this, we are going to like initially memory virtualization may seem like pretty straightforward, But at least by the end of this class, maybe you may understand like the complexity that you're going to get into. By the end of next class, I'm pretty sure you would really like appreciate the beauty that's happening in memory virtualization. Okay. So any other questions? Because this is the first part of the class, and the next part we are going to discuss one more mechanism called segmentation. And in the third part of the class, we're going to discuss some like introduction to paging, which most of you may already know, but again, you do that because we need.
And the addition to divide the physical address is done by the memory address. Is the addition to divide the physical address, that is an operation that is performed by the hardware?
Exactly, yeah. So that's a very good question. So this particular address translation, okay, this address translation that we are talking about here is actually performed by the circuitry that's inside the memory management unit. So basically the hardware does the address translation. Okay? The hardware really does the address translation.
And if a segmentation fault occurs, we tap into the OS, is that what happens? And the OS is what kills the process.
Exactly.
So the OS can choose not to kill the process if it comes.
Yeah. So if a segmentation fault happens, if a user process tries to access the virtual address 0, then immediately the hardware like says that this is trying to access this address, it knows that particular address. So immediately will trap into the like operating system. Once it traps into the operating system runs a trap handler. In this case, it will be like a seg fault handler, and the output will be just like kill the particular process, deallocate its memory from the process table, and just like. Any other questions? Yeah.
How does the OS pick the bounds value in the register?
What does it always take the bounds value?
How does it pick for like a given process, like user 16K space instead of like 32K or some larger number?
Yeah, so in this assumption, we are assuming that all processors are of equal size, okay? But when processors are of different sizes, then we have it in the proc structure or the PCB. We have the size of a particular process. So when we load a particular process, initially there will be like a size, and the process may increase in size when the stack and the heap actually grow. And so the size of that particular bounds of this particular process will be updated. But in this simple scheme, you may assume that every processors are just like 16K. But in the next scheme that we are going to see, we will see that there is going to be, we are going to change that particular value.
So it must have some default value.
Oh, exactly, yeah. So in this case, it's like the default value is always 16K. Okay, so there are no other questions. I think let's take a break right now. Let's take a 7-minute break. And
Yeah.
And I just placed any questions about the simple base and bounds relocation that we just saw. Okay. So the next scheme, so even before going to the next scheme, let's see like what are the disadvantages of this particular scheme. Usually when there is when a process is running, let's just take V2 here. Usually it has its code in the stack. Right. Usually what happens is for like normal user programs that are running, the address space is not completely filled up. Okay, even in this simple example, even though a process has a maximum of 16K addresses to access, usually it will be just like using just a little bit of the code segment. Only code segment will be just this much full. Okay, and then the heap may just start here, but it will be just a very small heap. And then for a stack, maybe the stack is just like this much. As of now, it's like. If this is the scenario, I mean, if the user processes really don't use up the entire code, the stack, and the heap, or the entire 16K address space that we have allocated for the particular process, then all this memory that lies within here, okay, all this memory that is like right here, And the memory that is between this the code segment, all these are just wasted. Okay. So even though in this setup we just saw like we can just run maybe maximum of 3 processes, but those 3 processes together may only use 16 KB of total memory. Okay, those 3 processes may in turn together maybe just use, they may only use 16 KB. We may have like 32 KB of memory in total that is left, but we may not be able to use it because they are stuck within these address spaces. And this particular problem of memory wastage, because we allocate a huge address space to a particular process, is called internal fragmentation. We have memory within each address space which cannot be used. So this base and bounds relocation really suffers of this problem called internal fragmentation. Which means again, just if P1 is only using 4K of memory, 4 kilobytes, then if P2 is only using 2 kilobytes of its actual 16K memory, if P3 is only using say 4 kilobytes, in total we have only using like 10 kilobytes, but we have allocated a total of 48 kilobytes for these 3 processes, because 16, 16, 16 each. And so the remaining 38 kilobytes of memory is actually wasted in this case. And so how can we avoid this particular problem? So the one way that people came up is, why are we the first main thing is like we were assuming that the program needs to be loaded in contiguous memory, in the physical memory, right? When we are loading a particular process in the physical memory, it should be in contiguous addresses. That is like a very big assumption. And so what people thought after some time was, why are we loading the entire program like this? We have these logical segments like the code segment, we have the heap segment and the stack segment. Why don't we just like load like a program segment by segment, in the sense, can we load the process P1's code segment somewhere, then the stack segment somewhere, the heap segment somewhere, and just keep track of where they are actually located. So this particular idea that we're going to look, it's called segmentation. Okay, this is the second mechanism that we are looking in address translation. Okay, like how virtual memory is actually implemented. So this was like a widely used mechanism a few years ago. And what happens here is, again, let's assume 0 to 16 KB. Let's assume the code is from 0 till 4 KB. It starts at 4 KB. Okay. As of now, let's assume the current size of the heap is 2 KB. So heap starts from 4 KB and runs till 6 KB minus 1. And let's also assume the current size of the stack is also 2 KB. Okay. We have a 4 KB size of code, we have 2 KB size of heap, and we also have a 2 KB sized stack. Okay. If this is the setup that we're having, all we're trying to do now is, let's assume the same physical memory setup that we had. So again, we are assuming physical memory runs from 0 till 64K. Divide this into 4 equal parts. 16K, 32K, 48K. And OS occupies this particular region, so I'm just reserved. In this setup, the question that we are trying to ask is, can we just, let's say, place the code somewhere here, okay? And we place the code starting at address 28K, okay? You can place the code here, the code is just placed here, and it is of size 4 bytes, sorry 4 KB, so it is right here. And if we can place the, let's say the heap, the heap can be placed somewhere, let's assume here at 48K, okay? Heap is placed here, and so from 48 to 50K we have the heap grows upward. Okay, code is fixed segment because it is the instructions, it doesn't grow or shrink, and so this is going to be fixed size of 4 KB. And let's assume we are placing the stack starting at, let's say, address 20. If you place the stack here, then it is going to occupy these addresses. This is the stack, and it is going like this. So a single program now can be split based on these logical segments called code, heap, and stack, and we may place these things at different parts in the address space. Okay. So the reason why we are doing this is we faced a problem called internal fragmentation when we placed a whole program like as it is, because a whole program just uses very little memory. But instead of just allocating that much, like let's say 4 KB or something like that, we were allocating a total of 16 KB for that particular process. But in this case, this process, even though its entire address space is of size 16 KB, the actual memory that it is going to use is just like 4 KB of code, 2 KB of heap, and 2 KB of stack, total of 8 KB. And the corresponding memory that it is occupying in the physical memory is also equal to the required usage. If you think about it, it also has like a code segment here which starts at 28K and runs till 32K. Code segment again increases upward, okay? The upward we mean it has like increasing addresses. And the heap is placed somewhere there, starting at 48 till 50, and the stack is placed somewhere here, okay? So in this setup, so a few things to note here are, okay, so when we say like this segment, this code segment is like upward going segment, and if it is placed at 28K, it means that, okay, the address 28K is actually used by the code segment, but this particular address 32K is not used by the code segment. It will be the maximum address of the code segment will be 32K minus 1. Okay, because the address space starts at 0 here. And even then, if you think about it, you are going from 0, and the maximum thing in the code segment will be 4K minus 1. That will give you a total of 4K addresses for the code segment. Okay? And when the stack is placed, and similar thing applies to the heap also. Heap starts at 48K and runs till 50K minus 1. Okay? The current valid addresses in the heap are 48K till 50K minus 1. But for the stack, since it is a downward growing segment, so stack, actually this is wrong. I just had like 4K for the stack completely, but the stack is only like 2K, right? According to our virtual stack will end at 18K. So just this is the stack, okay? This is free. This particular place is the stack. And in the stack, since it is a downward growing segment, okay, even though we say that the stack is placed at 20K, it really does not use that address at 20K. Okay, it cannot use the address at 20K. Stack can only start accessing address from 20K minus 1. But it can go till 18K. Okay? It can go till 18K. So now, in this particular setup, let's assume what is the hardware support that we may need. So for example, the hardware support that we needed for a base and bounce relocation was just like 2 extra registers from the hardware, the base, one base and one bounce register. In this setup, for making something like this work, Do you guys like understand the what to say, how useful this may be? Because like when another program comes in, we can easily place like the code of that particular let's say process 2 somewhere here in between this particular spot, and then the heap can be placed somewhere here, and it is like there is like no real ordering or like any what to say, particular rules for how do you place these things. Okay, it just is placed wherever there is some contiguous memory. But the memory here should be contiguous for the code segment. The code cannot be split up into multiple parts here. Okay, the code of a single process cannot be split up into multiple parts. The entire code segment for a single process should be placed contiguously, and that is the reason this is named as segmentation. You place the process's address spaces in terms of segments. You can place code somewhere, heap somewhere, and stack somewhere, and this reduces the internal fragmentation. But to help this work, to make this work, what may be the hardware support that we need?
2 additional pairs of base and bound registers.
Exactly. So we just need, in this case, we just need two more pairs of base and bounds registers, or in total we need 3 base registers and 3 bounds registers, one for each segment. So now our MMU, okay, memory management unit inside our hardware is just going to have like, just going to say something like this, bounds, and this is for the code, this is for the heap, and for the stack. I'm assuming this is one register, this is another register, this is another, something like this, okay? Just needs like these registers, like 3 base registers and 3 bounds registers for this particular thing. So in this particular setup, let's see what is going to be the values for this particular program. But before that, in the operating system, from the operating system's perspective, what should be added? In the prop data structure or in the PCB, we're just going to make that particular base and bound should be an array of size 3. Okay?
So, in the diagram we have here, theoretically the stack could grow to be 5K. And at that point we would hit the OS reserved physical memory space. What happens then?
So we have some restrictions here. Okay, that's a very good question. Okay. So first the question is, let's assume, okay, let's as of now assume that we have no limit of a maximum size of 16 KB, okay? If we assume this, that we have no, like, or let's say like the stack, the question was the stack can grow to a maximum size of, let's say 5K, okay? If it grows to 5 kilobytes of size, then what will happen? It may come and interfere with the operating system's address space here. So any ideas like what may happen at that time?
Reallocate another space.
Exactly. So we just like move that particular stack wherever there is like a contiguous region of 5 kilobytes of memory. So at that time, what is going to happen? That's a very good question. So when the stack grows more than 4 kilobytes, and if it cannot like accommodate here in this particular space, the operating system will maintain, internally the operating system maintains something called a free list. Okay, the operating system has a free list of memory regions that are free in the physical memory. So it knows at this time, from my free list I can see that the memory between 32K and 48K is like a whole chunk that is free. So I can easily place this particular stack, maybe starting at 48K, when it is growing bigger. Okay?
So, is the only reason that you can't fragment individual sections because we don't have enough base and bound registers? Like, if we had 6, could we divide the code into 2?
Exactly, yeah. So the only reason we cannot actually divide a segment into like multiple parts, let's say we can't keep like a part of the code segment somewhere and another part of the same code segment somewhere else, is just because we have no way to find out where that other part is. Because we only have a single base register for the code segment. We have a single base register for the heap, and similarly for the stack. That is the reason we have to place these things contiguously. Okay.
Does it anticipate any pre-allocation
for like our stack is, in this case, where we allocated 2 KB, when it got to like 1.9, would it anticipate like pre-allocating additional memory?
So usually those things happen in the sense, usually when we are like allocating, let's say even the stack was, let's say, just started at size 2 KB, operating system may not have placed it here because there is no space after that. It would have placed it in a much larger chunk of free memory where it can easily grow. Okay, so that is like considered as pre-allocation, but if we are saying like, let's say if the stack is just of size 2 KB, while it is placing it in the physical memory, it is not going to like pre-allocate more than that. But it depends on like the rounding of factors. So for example, you can't just allocate a single byte or something like that. There will be like a minimum chunk size that you can allocate. Even if you're allocating a size or a memory of size just 1 byte, it will actually give you at least a word size of 32 bytes. So in this setup, for like how this is placed, okay, if we are drawing the three the MMU, if we are drawing the, these are the base registers, these are the bound registers. This is for the core, this is for the heap, and this is for the stack. So the base of the code is going to be, since the code is starting at address 28, base is going to be 28K, and the bounds of code is going to be 4K. Because maximum size of code segment is 4K. And similarly, the base of the heap is going to be 48K, the base of the, and the bounds for heap is going to be 2K. Because current size of the heap segment is just 2K. And the stack, the base of the stack is going to be 20K, and the bounds of the stack is going to be 2K. Okay. So now, yeah.
Shouldn't it be 18K for the base of the stack, the lower range of the address?
Yeah, no. So it will be, so that in this particular system, like it will be like 820 will be the base of the register, but we will be seeing like how are we handling this in a sense, because it goes in an opposite direction, right? We can't use the same address translation mechanism that we are going to use for code and heap, because it completely goes in a different direction, grows in a different direction. Okay, so the base will be, okay, here we are assuming that, okay, here we are assuming in the virtual address space, okay, this particular thing that we are seeing here, we will name it as the virtual address space, okay. In the virtual address space that we have here, the stack is starting at the address 16 KB minus 1, 16K minus 1. Okay, and so this is the base of the stack, and the stack grows downwards. And here, the base of the stack is just placed at 20K, and so the register, the base of the stack register will only have 20K, and the size of the stack will be here in the bounds register. Okay. Now, let's take some sample addresses and let's see how we are going to convert them. Okay. The first address that we are going to take is, let's say, address, let's write it here, okay. The virtual address that we are trying, this particular process is trying to access is just address 1024, okay. First we need to figure out in which segment does this address lie in the virtual address space, and then find out its corresponding physical address. So when we say like the virtual address is 1024, the first thing that we will see here is in the code, it starts at 0, it goes till like 4 KB, right? And so 1024 is nothing but 1K, okay, or 1 KB. And so this is going to be somewhere between 0 and 4K. So 1K comes somewhere right here. And so we know that this is in the code segment. Okay, we have this address in the code segment. And to convert this to its physical address, okay, all we need to do is just go to its base. We know the base of this particular thing, which is 28K. 28K, just add this particular address that they're trying to access. After finding out it's in the port segment, just add it here, okay? And this becomes 29K. So 29K is the actual physical address that this program is trying to access currently. If you go and see here, it is just right somewhere here. Okay, 29K is here, it just maps to this particular address that we have here. Okay, so now, if the program, so this is like with respect to the code segment, this is the address in the code. Now let's take a virtual address. 4,200. Let's take this virtual address 4,200 and let's see like how are we going to find its physical address. First thing that we're going to do is we're going to find out where this virtual address lies in the virtual address space. So we know that the last virtual address of the code segment is nothing but 4 KB is 4096, so it's just 4096 minus 1. So 4095 is the last virtual address in the code segment. And so 4096 or 4K is the first virtual address in the heap segment. And it spans to 2K. So it's like 4096 plus 2024. So we are sure that 4200 will lie somewhere here. Okay? So if this is 4200, then 4200 lies right here, then how can we figure out its corresponding physical address? So can you try this? Based on all the information that we have, can you find out the physical address for the virtual address 4200, which we already found that it's in the heap segment? Take a few seconds to try it out. Okay, the first thing that we have to do here, is we can't just go and add this 4200 with the base of the heap segment, right? Because if we do that, the base of the heap is somewhere here and we will go like from here 4200 addresses. But all we have to do is find out, okay, the base of the heap starts at 4096, the base starts at 4K. So first you need to find out the offset, okay? You need to find out the offset from the start of the heap segment. The offset of this particular address 4200 from the base of the heap segment is nothing but this address, value of this address, minus the first address in the heap, which is 4096. And this comes out to 104, right? So this is the offset that we have. Now, you can assume that if the base of the heap, if it is 0, then the address that we are trying to find out is just 104 bytes away from this. Makes sense? And so what we are going to do is just go and say for the physical address, now you are just going to add the base of this particular heap, which is 48K. Just add this value of 104 to that particular base. Whatever you get is the actual value. And even in the exams, there will be a lot of questions like this, like in memory thing. You need not, if something is like this, you need not really compute the final value. Okay, you can just leave it right here. Okay, this should be fine. We are just trying to understand, like, not trying to do mathematical calculations.
So for the virtual address space, what's keeping track of where the code starts, where the heap starts? Is that the OS or is that the hardware that's doing it?
So for the virtual address space,
Because you're saying, well, they want this address, and we know that's a heap, so they go to the heap. How do we know that it's a heap?
that's a very good question. So the question is, okay, now we just saw like we are saying like, okay, this is from the particular, like the diagram that we have and the assumptions that we have, we are just saying like, okay, this particular address is in the heap right now or in the code right now, but how does the hardware really know which address are we trying to access? Because only if the hardware knows that particular segment in which that particular address falls into, it will be able to choose that particular set of base and bounds registers, right? And so, the way the hardware knows, let's for example take, let's say some, even this particular, these two addresses, okay? Let's just take these two addresses, 1024 and 4200, okay? And let's see like how the hardware looks at these things. Okay, so for that, first we need a few more things. We have a total virtual address space, okay? The virtual address space, size of the virtual address space is 16 KB, okay? 16 kilobytes. How many bits? This is like from a prerequisite 354. How many bits do we need to access 16 kilobytes of memory uniquely? 16. How many bits do we need to access this memory, or like how many bits are there in a single address? The virtual address. So we are going to write a virtual address here in binary form. How many bits it's going to have? Okay, can anyone say? So we may like split this up, okay? We may split this up into 16 times KB is nothing but 2 to the power of 10, right? These many bytes are there. So 16 is nothing but 2 to the power of 4 times 2 to the power of 10. So we have 2 to the power of 14 bytes in total. So for accessing 2 to the power of 14 bytes, we need 14 bits basically. Okay? Simple way to understand this is if we just have, let's say, 4 bytes, 0, 1, 2, 3, 4. If we just have 4 bytes in total, we need 4 is nothing but 2 to the power of 2, right? 2 to the power of 2 bytes. So we need at least 2 bits to access 4 bytes. So the 2 bits are going to be 0, 0, 0, 1, 1, 0, and 1, 1. Okay? We need at minimum 2 bits to access 4 bytes uniquely. In a similar way, if you want to access 16 KB, which is nothing but 2 to the power of 14 bytes, we need 14 bits. Okay? We really need 14 bits. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay? Now, the places are 1, 2, 4, 8. The values in binary, the position values in binary, I'm writing down here. 32, 64. 6,000, this is like 512, 1,024, okay, which is nothing but 2 to the power of 10, then 2 to the power of 11, 2 to the power of 12, and 2 to the power of 13. Okay, this is how our address is going to look like. So now if the task that we are trying to do is like make our address of 1024 in binary. The simplest way to do is like this has a value, this particular position has a value of 1024, we just mark a 1 there, okay, and make all the other things to be 0. So now this particular address just corresponds to the this binary address corresponds to the value of 1024. Okay, or this is the binary for 1024, and I have divided them into like 4, 4, 4, and the final two things are just 2 bits here. Okay, the reason is usually we write these addresses in hexadecimal. This is going to be 0, 0. This is going to be in hexadecimal. This is going to be again 1. This position is 1, 2, and 4. This is 4, and this is 0. So this address, write it in hexadecimal, it is nothing but 0400. Okay, makes sense? Now we have it here, okay? So, one thing from this, okay? The hardware uses the most significant bits, the two. We have 3 segments, core, heap, and stack. So at least we need 2 bits to uniquely identify these 3 segments. So right, if we have only 2 segments, we just need a single bit. Just say 0 means core and 1 means other segment or something like that. But we have 3 segments here, core, stack, and heap, so we need at least 2 bits to uniquely identify these 3 segments. So in this case, the 2 bits are these most significant bits, okay? The most significant 2 bits, if they are 0, okay? So 2 MSBs, in this case, okay? If they are 0, 0, then the segment that they are corresponding to is just the core segment, okay? And if the most significant bits, if they are 0, 1, then they correspond to the heap segment. And if the most significant bits are 1, 1, they correspond to the stack segment. Just think about this, this would really make sense because again, this is assuming a few things, okay? This particular scheme of segmentation is assuming that, okay, the code lies here. We have this entire 16 thing. This is 0 through 4. This is the code. And the heap can start here. Stack can start here. In this particular scheme, okay, so 0, 4, 8, 12, 16. Okay. In this particular scheme that we have, there is a maximum size for each segment. Okay, a single segment cannot be more than 4 KB. In this scheme that we have, a single segment cannot be more than 4 KB. Yeah.
So when you say the 2 most significant bits, you mean bits like 14, 15 that are kind of off the page?
Yeah, the leftmost 2 bits.
12 and 13.
Because, yeah.
2 power 12 and 2 power 13, yeah. Because we start at 2 power 0.
But what if the stack goes past 1, 1 as the most significant bits?
Oh, never mind.
Yeah, so in this case, we really can't, the maximum size of the stack is 4 KB. So in this particular scheme that we are discussing, okay, we have some limitations in segmentation. When we are like dividing it like this, so usually, okay, since like in this case, okay, this part in the middle from 8K to 12K is actually unused. Because that particular part, if you think about it, is going to have the most significant bits to be 1, 0. Okay, we are not mapping that to any of the segments. So the maximum size a stack or a heap can grow in this particular scheme is only 4 KB, and maximum size of core segment is also 4 KB. Okay. So with this, now you may also try, if you try converting the address 4200, okay, 4200 to binary. Let's see what's happening. Let's just convert it to hexadecimal directly. 16, 2s are 32, so 10, 16, 9s, 16, 6 are 96, 40, 16, 2s are 32, get 8 as a reminder, 16 1s are 16, then you have like 10 here, 102, 16, 6 are 96, you have 6 here, then you have 16, 16 1s are 16, 0. So just divided it by 16, each number, and I just got the reminder right here. And so this number, 4200, if you just convert it into hexadecimal, it just becomes 0x. You have to start writing it from here, 1068, okay? So 1068 is this number in hexadecimal. Now if I just want to write this number in binary, all I'm going to do is just take bit by bit. I just take this 8 and have it as 4 bits here. So this is 1, 2, 4, 8, right? So 1, 0, 0, 0. Then the second part is going to be 6. This is 8. 6 is 4, 5, 6. This is 6. Then the third part is just going to be 0, all zeros. And the last part is just going to be, you may just have like 2 bits there, that's enough, because you only have 14 bits in total, right? Just can have 2 bits, so 1 just represented in 2 bits. So can you see here? Now the last to the most 2 significant bits are 0, 1. Okay, and the hardware will just see these most significant 2 bits and find out it is in the heap segment.
This might sound silly, but I'm gonna guess that there's a whole lot of this kind of thing on the test. So is there a good way to practice this, or like something we can go to do more of this?
Practice what?
Converting addresses and things in binary.
Oh, okay, you need not worry. So in the test, we will not be asking you to convert like these things right away. Maybe even if you are like doing it, will be dealing at the level of like KB and stuff like that. We will make sure, like while preparing the test, we will make sure to keep this as minimal as possible. Okay, definitely like conversion like this directly from a decimal to hexadecimal, we will not expect on the exam. So for example, but if you can, it will be, what to say, but at least with this idea, you should be able to get it in the sense, what we did here, right? So we did not really convert, we just like used the positional values to actually come up with the binary or something like that.
Sure, yeah, makes sense.
So definitely we will try to decrease the math behind stuff as much as possible, okay, in the exams. But I'm not saying it will not be there because definitely these will involve some math because in some cases we had something like we gave everything in hexadecimal and if you can figure out like what to say, if you can figure out, there are like some, I can show you some questions maybe at the end. In those questions, if you can draw some diagrams and figure out like where they are or something like that, at a high level, that may be enough instead of just converting everything into it. Okay, so we have this, and so we found that this is in the thing. And now let's take an address in the stack segment, because segmentation gets more interesting when we actually move to the stack segment. Okay. So is everything clear till now? Any questions? Because from now we are going to like add just more complexity, each and everything as we proceed.
So basically, like the stack just grows past that point, just the program is stable, and you want to really.
Exactly. So in this particular case, yeah. So in this particular case, when a stack grows more than 4 KB of allocated memory, okay, it will be just a stack overflow. In this case, because it is going to hit this particular unused memory region that we have in the middle. The stack is going to hit this memory region that is actually not valid memory according to the program. Okay, and so whenever program crosses 4 KB of stack usage, immediately it's going to be stack overflow, and then your program is going to crash. Pardon? Yeah, exactly. Even for the heap, in this particular setup, you can't allocate more than 4096 bytes on the heap.
So that means all of these segments are going to be 1/4 of the size of the.
In this scheme, yes, yeah.
In this, we are using the MSB
Yeah.
to indicate which segment.
Exactly, that's a very good interpretation. Since we are using the two MSBs to identify which segment that particular address falls into, any segment cannot be more than 1/2 of the total address space. Because in 2 bits you can represent like 4 values, right? 00, 01, 10 and 11. So it is, those 2 bits are actually dividing the address space into 4 equal halves. That is the main idea here. Pardon? Yeah, sorry, 4 quarters of equal size, yeah. 4 parts of equal size, yeah, not halves, yeah. Any other questions?
And in this scheme, you have that unused portion. If you have more than one program loaded into memory, could that be used by a segment that belongs to a different process?
Okay, that's a very good question. So the question is, can we use this unused portion? Okay, can a different program use this unused portion? Yeah.
Isn't it virtual memories, like that's not even allocated in the first place?
Exactly. So that's the answer there. So the answer is, the thing that we're seeing here is the virtual memory. So by that we mean, even though we have a total of 16 KB for this particular process, in the actual physical memory,
The segments are somewhere else, so we don't really.
yeah, the segments are somewhere else, but only 12 KB. If every segment is at its maximum, even at that time, only a total of 12 KB is going to be used by this particular process. Because we are not even going to allocate some memory for this space between 8 KB to 12 KB in the physical memory. Because that's memory wastage, right? Question?
But that means that the process can't be unused.
Yeah, the process can't use it. In this case, the process can't use it. But if you think about it, the segmentation in the real world will not just have something like 16K, okay? It will be having address spaces of 4 GB. Okay, single address space will be of size 4 GB. So we really need not worry about the issues that we are currently focusing on. Because with the address space of size 4 GB, like no process is really going to use entire address space. So in that case, a single segment will be of size 1 GB. You can have a stack of size 1 GB, just think about it. Okay? So there in the real world scenarios, these are not real problems. And that's why segmentation works in a very good way. This really works. Okay? And even there, the main thing is even though a single segment's maximum size is 1 GB, when if that particular segment is of size only 1 KB at a time, we are only going to allocate 1 KB memory in the physical memory. We are not going to allocate 1 GB for that particular segment. That's the whole like the benefit that we're getting due to like virtualizing memory. And in this way, in a segmented way. Just think about if we are going to allocate the 4 GB size of virtual memory or address space in the base and the bounds register, in the base and the bounds scheme, relocation scheme that we just saw before. If your total memory is, let's say, just 4 GB in total, OS may occupy some part in it, you may not even be able to run a single program in that case. If you want to just place the entire 4 GB in the physical memory before executing it.
So, and this baby's getting to like tables and stuff, but if you had 4 GB of addressing, like, you really try to just represent that as an address.
Yeah, so
As soon as I was the tables,
exactly. The question was if there is like a 4 GB of address space, what may be like how many bits we may need to a single virtual address may be how long, right? This is the question. So in 4 GB, as we just saw, we already saw GB is nothing but 2 to the power of 30. This is nothing but 2 to the power of 32. So each virtual address is going to be of size 32 bits in a 4 GB address space. Okay? I think it's 7:30 because next thing is like really important. How are we going to like find out the physical address in a stack segment? So I think we'll take a break right now, and then you may like work this out later, but this just corresponds to 3C00. Okay, this address 15 KB in hexadecimal. This corresponds to 3C00. If you want to like write it here, it's going to be first the 0 here and then the 0. C is nothing but 12, so it's like 8, 9, 10, 11, 12. Actually, these are not very useful right now since you're not doing the conversion. But yeah, this is like C is like. So when we are considering within a single thing, this just maps to like 1, 2, 4, and 8. So 8 plus 4 is 12, and then so decimal C just corresponds to 12. Okay? And then here we have 1, 1 because we have the value of 3 here. Okay, 3 just corresponds to 1, 1 in hexadecimal. So in binary there. Okay. So now with this we can easily find out. Okay, hardware can figure out with these two segments, with these two values, 1, 1, it is in the this particular address is in the stack segment. Okay. Now after that, what can we do? So like with this particular information, as human beings, we can easily see that okay, now we have loaded that stack of size 2 KB, okay, of size 2 KB from there, and it is like not to scale, okay, because the 15 KB there should have come like right in the middle, but I just drew something somewhere on the top. So now let's assume that the whole stack is placed right here. As human beings, we can easily see that, okay, the address 16 KB is corresponding to the address 20 KB here, right? And the address, so 15 KB is just going to be 1 KB below that. So we can easily see from here, we can easily find, because we have this visual view, you can say that this is just the address that we are going to, the physical address of this 15 KB is nothing but 19 KB in the physical memory. Is that right? But internally, the hardware does not have this pictorial view of stuff, right? It needs to, just with that particular address, it needs to figure out where this is in the physical memory. So, how does it do that is, now it takes this remaining part, okay? It takes this remaining part, first it figures out this is these two things just mean they are in stack segment, and in this remaining part, now let's just try to add this up, okay? Try to find the value of these 12 bits. So it's just 2 to the power of 11. Now as a whole thing, okay? We're trying to find it out as a whole 12-bit number, okay? So it's just 2 to the power of 11 plus 2 to the power of 10, which is nothing but 2 to the power of 10 times 2 plus 1, right? So it is 3k. 3 into the power of 10 just stands for k, which is 3k. So this 12-bit number just corresponds to 3k. So again, so now the hardware knows, okay? Let's assume the hardware knows that the stack is starting in the physical memory, the stack is starting at 20k. It has found that it's a stack, so it can go to this location easily because it has its register for base register for the stack. It goes to this 20k. But after that, to find out 19k, the way that the hardware uses is that it goes down for the entire maximum size of the stack segment. So in this case, in this scheme, the maximum size of the stack segment is 4 KB, right? So it just tries to go down, let's say, to this particular spot, okay, 16k, okay, tries to go down here. And since this is the maximum size of the stack segment, now you may consider this particular 16k to be the base, as the base of the code or the heap as it is like growing up or something like that. You understand? So now we have gone to the base of this particular segment because the stack is going to be contiguous. That is like a very important assumption here. Because the stack is going to be contiguous, now you may think like I am subtracting, okay, from the base, okay, I have the base register, is 20k. Just subtracting the max size of the stack segment. Subtracting max size of the stack segment, which is nothing but 4k. Now I have got like 16k. Now to that I'm just adding, okay, I'm just adding whatever offset that I got here. This particular thing is nothing but, so you may name it somehow, okay, I'll just have this offset, okay, which is nothing but 3k. Okay, so this just this calculation for the physical address. You think about it. You came here and then you jumped back, this first thing that you did, then you added 3k to it, so you jumped back, in the second step you jumped here, so now you are at 19k. Now this just corresponds to 20k is the base, minus 4k plus 3k. So actually, if the usual formula is just like base plus bounds, okay, base plus, not the bounds, sorry, base plus the offset, okay, base plus the offset, here you are getting, you may consider this also as offset, but actually the offset here is this entire thing, okay? This entire thing. So the offset here is actually minus 1k, okay? We are getting a negative offset for the stack segment. And so this is going to be 19k.
Why can't we have just taken, I guess, 1k as an offset from the get-go, because we need at the top of our stack and virtual memory is 16 KB. And our address is 15 KB, so like we would get a 1k. Or why not just, I guess, like why go through everything else?
So yeah, but the only thing is here is like we are knowing these values in terms of 16k and 15k, but the hardware only looks at that like bit pattern. From that particular bit pattern, how can the hardware infer that 1k? You understand? There is no way for the hardware to infer that the address that I am looking at is just like 1k away from the top, just looking at the bit pattern. So that's why it tries to understand from the initial offset that we got, okay, maybe we'll name it as something different because like this is like let's just name this as initial offset or something because this is not the actual offset, okay? This is the initial offset that you have here, and this offset is actually from the base, okay? This is like 3K from the base, and so from this offset you're computing the the maximum size. You just subtract it and then go to that particular thing. So you basically. So important thing to understand here is like the hardware only looks at this. It has no idea about it. It knows that it is loaded at 20K. It knows that. It also knows that the virtual, but it has no idea that the address that we're trying to access is just 1K below the top of the stack. Okay. Since the hardware has no idea about how the stack is organized in the virtual address space, where this address lies exactly in the stack, hardware can't do simple calculations as we can do. And that is the reason it is following this particular strategy. Yeah.
Does the hardware know if the max partition is going to be 4 kilobytes? So how do they know that it's that bigger part, it's a smaller part of that bigger part? So you're saying like if we have to say go to the base of the stack, which is minus 4K, how do we know minus 4K? Is that just something that's set on?
So it is like, so okay, this is also a very good question. So as we just spoke, like on a 32-bit machine, okay, it is like architecture dependent. On a 32-bit machine, the maximum address space is going to be 4 GB for virtual address space. In that, the maximum, if you're using this scheme, the maximum stack size is going to be 1 GB. Those things are like hardware, architecture-specific constants for that particular machine. One more interesting thing. So the hardware does like this address translation for a code or a heap or a stack, okay? But how does it, like what to say, how can it figure out that if it is a stack address, okay, if it is an address on the stack, it should do a different calculation. You see, like, what I'm trying to ask?
If you're doing this for the heap, it would just be the same except it grows the other way, so it's plus the size of the heap segment.
Exactly. So, no, for the heap, it's just going to be as we just did before. You just subtract you just find out the offset from the base of the heap and just add that offset directly to the base of the heap in the physical memory. It's going to be like that. So, it does it different ways for a growing segment and for like a decreasing segment, right?
Does it just use the 13th bit to say if it goes up? Does it have to subtract? Because that's the only one that's set to the stack.
Yeah, but even with that particular bit, with those 2 bits, okay, it can find out it is in the stack segment. But how can it find out the stack segment is growing downwards? Because if a segment is growing downwards, it needs to apply this particular formula to calculate the physical address. If a segment is growing upward, like a code or a heap, it just needs to do the other thing, right? Just adding the base with the offset.
Why can't you just hardwire it to be when the 1-1 is going down? Like, that's the first you did.
I thought the stack always grows downward, but that was a convention.
Yeah, so that is also not needed, yeah. So
that could go upwards?
yeah, exactly. So that's a very good question again. So why can't we just hardwire in the hardware just to say something like whenever it's a stack segment, you may just assume that you have to perform this particular calculation, because in some places it's not like really necessary to have the stack always grow downward. You can have an address space like the code, then let's say immediately stack on top of it which grows upward. It is also possible. In that particular place, the heap will be the segment that is growing down. Does it make sense? So it is these things that we're talking about are like used in most of the systems. So that's one thing is like in XV6, when you're going to look at the address space of XV6 process, it's going to be like this. There is like a 1 page of it's like some space for the code segment, and then there is just like some space for the stack segment, and it is also fixed in the sense stack cannot grow more than this currently. In XV6, okay? In XV6 it is like this.
So is that operating system specific or hardware specific?
It's operating system specific, yeah. It is operating system.
When it looks boots, does the operating system select all hardware?
Yeah, exactly. Which are the Yeah. So that's what you're going to see here. So and in XV6 it's like this. XV6 address space looks like this. We have a fixed code in the sense it is like this is just like 4K, and this is also 4K, and heap starts I think at 4K, or then it can grow upward. But the stack is like fixed, it can have only 4K. So if you're just doing like a recursive call in XV6 in a C program, then immediately it's going to crash. Because it can't grow more than 4K, your stack in XV6, okay?
Is it up or down in this case?
It's
So the
up,
stack
yeah, it's up here.
Stack goes up.
Exactly, here it just goes up, yeah. So in XV6 it's like this. And one fun thing is like one of your projects, like the next project for what say in memory management in XV6 is going to be like you are going to like make this stack move here as we see in the normal address spaces and make it grow down. It'll be so much fun again. So you're just going to like place this from here to here, and you will have the code, and then immediately this heap will start as we just discussed till now, as it is in Linux. We will be converting this particular address space to something like that. Okay? And so how the hardware takes care of this particular thing here is, okay, along with these, so we just saw some things like we have the base, we have the bones for each thing, right? Along for each segment, right? So this is the segment. So this is, let's see, the code, the heap, the stack. Now along with these two things, it also has an additional like space for something like a bit for growing up, something like this. Okay. So here for the core segment is going to be 1, for the heap segment is going to be 1, for the stack segment is going to be 0. And this is how the hardware figures out, using these additional bit values or registers, the hardware figures out how can we calculate the particular address for that particular segment. And along with that, it may also have some things for permissions. The code segment can be read and can be executed, but no one should be able to write to a code segment. And so it will also have bits for these permissions here, but a heap can be read and returned, but should not be executable, right? And similarly, a stack segment can also be read and returned, but we should not be able to execute something in the stack. All these bits will also be there for each and every segment. And these are the additional hardware support that the hardware provides for the segmentation to work properly.
So does the OS have to tell the hardware what those values should be?
Exactly, there will be a communication from the OS to the hardware, yeah.
Are there any real operating systems that actually implement it like this, where each segment is kind of allocated a contiguous space of up to a quarter of the address space, or is this more so just like a theoretical example?
So I don't like remember any names of the operating systems, but this was like actually that it was implemented a few years before when this was the idea that was like in use before paging, the segmentation, yeah. I can check that out if the names of the operating systems. Yeah.
Can you go back to when you calculated like the base minus the 4 plus the offset?
Yeah.
You said earlier that if you could have, like 4 kilobytes of actual memory for the stack, like it might not initialize all 4 in the beginning.
Yeah.
If that's the case, how does it know what to subtract and where to go?
Great question. Yeah. So that's a very good question. Okay. So what happens in this case? Okay, if the address that we are trying to access is, let's say, 13 KB. Okay. If someone is trying to access 13 KB, which is also on the stack. Okay. But currently the stack is only full till here. Okay. We assume that currently the stack is only full till here. This is like invalid address currently. Okay. Currently this is an invalid address. 13 KB is an invalid address. What will happen here if you do this particular arithmetic? Exactly. So what is going to happen is, first you are going to calculate this difference, right? So from this particular thing, you will be calculating some offset, right? Okay, that offset, and after you calculate this negative offset, it's going to say minus 3k, correct? Is that correct? It's going to say minus 3k, and immediately you will check that value of absolute value of 3k with the bounce register. In the bounce register, we had the value to be 2, because the maximum size of the segment was just 2, and so the value would be 2 in the bounce register. See here, we'll go here to the bounce register, check that absolute value. In this case, we would have actually checked this absolute value of 1k with the bounce register, which is 2k, which is less than that, so it's fine. You can, this is a valid address in the stack, and you will actually do the translation. But if this was like 3k, which is greater than this bounce of the stack, then it knows that it may fall in the stack segment, but it is not yet an allocated address. And so it's going to set for it.
Wait, so I might have missed this part, so where did we get the 4K from that we were subtracting?
4k is just the maximum size of a segment.
Is that stored in the MMU anywhere, or is that just decided at the OS level?
So it's like a thing, for example, each mission, so for example, if this computer if it is like a 32-bit mission, we say like we define a mission as a 32-bit mission, which means that the virtual addresses are of size 32 bits. Based on that, we can calculate the particular. And it will be like internal parameters.
Why would the bound be less than the stock, like the size of the segment? Maybe that's like why would
Why would the bounds be less than the maximum size of the segment is because the bounds in a segmentation scheme does not give you the entire size of the particular segment, but it just gives you the length of the size of the valid addresses in that particular segment. So since in this case our stack was only of size 2 KB, since our stack was only, even though it could have grown till 4 KB, but currently it is of size only 2 KB, the bounds will only have 2 KB.
So this access fault that we would get, this is because we're trying to like access it, but we haven't yet allocated it yet.
Exactly, yeah.
Did you theoretically like have allocated it, or like how that makes it sound like I want more?
You could do that, yeah. So in this case, your stack can grow up till 4 KB. So there are 2 KB extra space in the stack.
Yeah, so so every time we're growing the stack, we're updating the bounds.
Exactly, yeah. So every time you're growing the stack or the heap, or even like decrementing, I mean like reallocating something from the heap and stuff, we are going, the bounds register is going to be updated. Because that is now attribute of the particular process.
So there's also the maximum stored elsewhere based on the architecture.
Yeah, exactly.
Is it the OS or the hardware?
Yeah, the architecture, operating system, hardware.
So it is actually like mostly hardware, but there will be like some interaction from the operating system. So for example, on the same mission, we can actually, even if it is a 64-bit mission, okay, we can run programs saying like consider it to be a 32-bit mission and compile this program in that way or something like that. The operating system can like it is like I would say it's a combination of both. It's not just a single.
My question was for growing basically changing the bounds of the stack and the segments. Is that mainly the OS or is that the hardware or is it kind of combination?
Oh yeah, so the changing the registers, the bounds and the the bounds registers values the operating system does.
So every time you do the stack pointer change, the whole operating system has to update.
Exactly. So it understands it from the memory allocations. This program is doing memory allocation, so it's allocating this much memory. So it is stack grown this much to update the bounds of the stack. Okay. So in this particular scheme, okay, one of the important. Right, this seems to be a great scheme, right? So, are there any disadvantages that you can think of in this scheme? Because we are not going to stop here anyways. So, if you think about it, let's assume this is like some memory. say P1's code is here, then process 1's heap is here, then process 1's stack is here. And let's say this is OS, okay? And we may assume that we need to load, okay? We need to load, let's say, just process 2's code segment, okay? Process 2's code. This is of size 4K. If process 2's code is of size 8K, this is like some assumption, you need not worry about any of the other things here. If process 2's code segment is of size 8K, then in this case we will not be able to load the process 2's code segment, even though there is a total size of 8 KB that's there. Okay? Now you may not assume that a process can have only 4 KB of code segment. Okay, we can assume, like, we just leave that assumption. And if we are assuming that a process can have like 8 KB, then in this particular scheme, even though there is like 8 KB of space or even more than that, let's assume that maybe even a 4 KB here. Even if there is a 4 KB here, even though we have 12 KB more than whatever we need for loading the code for this particular process, we would not be able to load the code segment of P2 at this time, and the process would be just waiting to run. The operating system would not be able to execute that particular process. So this particular problem, this fragmentation is called external fragmentation. That is the memory that is lying in between the different segments, which together add up to be like a lot more than we actually need. But since, what is the problem here? The problem is we cannot split this particular code segment into multiple parts, basically, right? Even though there are like 4 KB here and 4 KB here, we cannot split this code segment into 2 parts because we just have a single base register for the code segment. And we have to store it contiguously. And so this is where what we could do is take an address space of a particular process. For simplicity, let's make it even smaller, okay? Just 0 till 16 bytes, maximum thing is 15, okay? Total of 16 bytes. We only have an address space of say 16 bytes here, okay? Just split it into, don't worry about the logical segments, okay? The next idea or the idea that is being currently used is just, don't worry about the logical segments of code, stack or heap or anything like that. Just split this entire address space. This is your virtual address space, right? Just split your entire address space into equal sized chunks. In this case, we are going to consider the equal sized chunks to be just, let's say, of size 4 bytes, okay? This is chunk 1, chunk 2, chunk 3, chunk 4, okay? And these chunks in this particular scheme, the scheme that we are going to see, are called pages. This is nothing but page 0, page 1, page 2, and page 3. Okay? And each has like a unique number. This is called the virtual page number. This is the virtual page of this particular process. And it has virtual page number 0, virtual page number 1, virtual page number 2, and virtual page number 3. So in this scheme, this particular scheme, this is called, since we are dividing them into equal sized pages, this is called paging. Okay. So now what happens? Now let's assume our memory to be of size, again, unrealistically small, like say 32 bytes, okay? Maybe slightly more, 64 bytes. Let's assume we have an operating system, the smallest operating system of size 16 bytes, okay? We have this operating system here, and then we have like this space is available, but the important thing here is like even this particular space that we have will be divided into the page sizes, okay? So the physical memory will also be divided into page sizes, so this particular portion that we have here will actually be, has 4 pages in it, because each page is just like a 4 pages again, then 4 pages here, and this, and when you divide the physical memory in page sizes, let's say this starts at 16, now this is 20, right? So this is called a virtual page number. Sorry, this is the virtual page number. This is called a physical frame number, PFN. When you divide the physical memory into page sizes, it's called a physical frame number. And so even this particular part would have been divided into 4, basically. Okay, even though it's occupied either way, so this is going to be a physical frame number 0, then physical frame number 1, then 2, 3, this is 4. Okay, so now the scheme is like so flexible, you can place any virtual page in any physical frame here. Okay, you can place basically any virtual page of this process. Let's assume we place like the virtual page number 0 right here, okay? Then, so it means that this page is placed here. Then let's place the virtual page number 1 here, then virtual page number 2 here, and virtual page number 3 here. That's it. So now this, again, the reason this was introduced is to just avoid the problem of external fragmentation. Since we are dividing this into like minute or like a fine-grained size of pages, and you can now use your entire physical memory as much as possible when compared to segmentation. So definitely the external fragmentation is largely decreased.
Theoretically, like there'd be code in 0, you keep 0 in 1.
Exactly, yeah. So that's a very good question again. So the question was like, theoretically, can there be code in, let's say, page 0 and page 1? Yes, it is possible. Okay, page 0 and page 1 can have the code in it. So the concept of segments completely, like goes away when you go to paging, because even a single page can have things from multiple segments. Okay, even a single page here, let's say page 1 can have part of the code segment and part of the heap segment there, part of the heap there. And so we will not be thinking about in terms of logical segments anymore. Once we start paging, we will just think of the whole address space as a single chunk. Okay, and then just like try to access each and every address specifically. So let's see. So now what do you think maybe the hardware support that we need to make this scheme work? Initially we just needed one base register and one bounce register. In the second segmentation scheme, we needed like 3 base registers and 3 bounce registers, along with that a few more bits for growing positive or negative and stuff like that. In this particular scheme, what do you think would be needed? So if you think about it, yeah.
Register for every page?
Pardon?
You need one for every page.
Exactly. So one of the ideas is like you need like a single register for each and every page, which stores where this particular page is stored in the physical memory, okay? But the problem here is, okay, this is like a very small address space again. So the problem comes like when we are talking about address spaces of size, real world address spaces of 4 GB, okay? So now what happens is, in a real world address space of size 4 GB, we already saw that we need 32 bits to store for a single virtual address, okay? And a page size in a real world machine is usually 4 KB, okay? So, which is nothing but, so therefore, if this is the total size of a single address space, okay, this whole thing is 4 GB. If a single page is of size, one page is of size 4 KB, then how many pages do you have for each and every process? Think about this, okay? The number of pages that we have, the number of virtual pages that we have for each and every process is going to be 4 GB, the total size of the address space divided by the size of a single page, 4 KB, which is nothing but 4 times 2 to the power of 30 times 4 times 2 to the power of 10. Okay? It's nothing but 2 to the power of 20, or approximately 1 million virtual pages. So we'll be having 1 million virtual pages for a single process, okay? Then just think about it. If the hardware needs to support this, then it needs to give us like 1 million registers to find out where each of these pages is, which is like not possible, right? I mean, it's possible, but it's like not efficient. And so, and usually people try to keep the hardware as simple as possible. So definitely they're not going to do this, even if you give this request to the hardware, like architecture people, okay? So in this case, what is going to happen is, now, since these mappings are like so huge, we need like so many different mappings, the operating system takes the responsibility. The operating system says, okay, till now, since segmentation and even so the first one, the base and the bounds relocation and the segmentation, they were like pretty simple, so we were able to manage it with the hardware support. But I think in this case, I would take the responsibility. I would make sure that the operating system is saying, I would make sure that I would have like a mapping. So all I need here in the simple scheme is just a mapping from the virtual page number to the physical frame number, right? Where this corresponding virtual page is placed. So all it needs is just saying like 0, 1, 2, 1, 3, and the physical frame number, where is virtual page 0 at 11, and 1 is at 8, 2 is at 12, and 3 is at 6. That needs to be a data structure like this, okay? But maybe it just has like 1 million rows, okay? That's fine, but I will just create a data structure. Like this is just a table, right? A linear table. And so the operating system takes care of it, and this particular data structure in the operating system is called the page table. It's just the page table. It stores the translations between the virtual page numbers and the physical frame numbers, where each and every virtual page is placed. In the real world, you may assume that this may run from the virtual page numbers, may run from 0 till 2 to the power of 20 minus 1. Okay, if we are using like the paging scheme. But technically, that uses up a lot of memory, okay? So, okay, technically that uses up a lot of memory. If you see here, we just calculated that 1 million pages, right? Just think about if we have like 1 million pages, which is 2 to the power of 20, and if each entry in this page table, okay, this particular entry, each entry in this page table is called a page table entry, PTE. For each entry is called a page table entry. If we assume like for a single entry, if we need 4 bytes, like integer size, okay, if we need 4 bytes for each page table entry, the size of this page table is just 16 bytes in total, but the size of the real world page table is going to be 2 to the power of 20 times 4, which is going to be 4 MB. It is like unrealistically large, just for storing a page table of size, because we were talking like the operating system itself in total takes like 4 MB of memory. It just needs like 4 MB for storing a single page table. Okay, why did I use the term single page table? Is because this page table that you're seeing here is a per process data structure. Per process data structure. Because we can easily see that if we have another process called P2, that process's pages can be mapped completely differently at different physical frames, right? So, each and every process, operating system maintains a page table for each and every process separately. And so, when and where do these page tables reside? These page tables just reside in the OSS memory here. Okay, we have the OSS memory here, right? You may assume that this page table was right here, somewhere here. So it will be like something like in the OSS memory, it will be like page table for process 1. It will have the values like 11, 8, 12, and 6. It will actually not even have these virtual page numbers in the actual page tables, because since it is arranged linearly, okay, it will just understand that the first entry is for the virtual page 0. Second entry is for the virtual page 1. It's just like a linear page table, linear array-based page table. You need not even store the virtual page numbers. You can just use the index of that array to be the index of the virtual page. Okay? And it will be stored in the OS's memory here. Okay? And now let's do like a simple address translation here. Now, if we want to find out what is the physical address, okay? We want to find out the physical address for a virtual address. For a virtual address is, let's assume it to be just 10, okay? For a virtual address 10, what is the physical address in this corresponding scheme? So the first thing is, how many bytes does a virtual address take? Because you only have 16 bytes of virtual address space. A virtual address is going to take 2 to the power of 4 bytes. So virtual address is just going to take 4 bits here, okay? In this simple scheme. So you can just represent 10 in 4 bits. 1, 2, 4, 8. So it's just going to be 1, 0, 1, 0. Now, okay, how do we find out the physical address here is, we know like a page size, right? So page size in this case is 4 bytes. So based on this, we just say 2 to the power of 2 bytes. So you just take this 2. So you have, like in this case, we have 4 pages. So this just tells you how many bits do we need to uniquely identify each and every page. Okay, to uniquely identify each and every page, we need minimum of 2 bits. So what we're going to do is, we are going to divide this address, okay, that we have into 2 parts. Like the 2 bits that we need for finding out the page is called the virtual page number. This is going to give us the virtual page number, okay? These 2 bits, the most significant 2 bits are going to give us the virtual page number, and the remaining bits are going to give us, this whole thing is going to give us the offset within that virtual page. And so this virtual page number just corresponds to 2, right? This just corresponds to 2. So it just means we need to look up. So the virtual page number is just 2. And so go to your page table, go and find the mapping for the virtual page 2, virtual page number 2, the virtual page number 2. We found out that it is 12. So take that number 12, okay? Take that number 12 and just, let's say, we pass it to something like address translation. Address translation takes this virtual page number as the input and produces the number 12, which is the physical frame number as the output. Okay? When it does this, now we need to figure out the actual physical address. For doing that again, so in our physical memory, what is the number of bits that are needed to represent a physical address uniquely? We have like a total of 0 till 64 bytes, right? So we need 6 bits basically. We need 6 bits to represent a physical address. So physical address is going to have 6 bits, 2, 3, 4, 5, 6, okay? And then, and a physical frame number, okay? Physical frame number can go from 0 till 15, okay? Physical frame number can go from 0 till 15. And so we need at least 4 bits to represent a physical frame number uniquely. So in the physical address, we are just going to divide this into 2 parts. This is the physical frame number, which has 4 bits, because we have a total of 16 physical frames, 0 till 15. Okay, so we need at least 4 bits to represent the physical frame number, and then the remaining bits is just the offset bits. So once this address translation is done, using the page table, okay, using the page table, after we do this, just make this 20, write this 20 as a 4-bit number, 12, so write this 12 as a 4-bit number here. So it is just like 1, 2, 4, 8, right? If you write 12 here as a 4-bit number, it's going to be 1, 1, 0, 0, and then the offset just comes directly from there. offset just comes direct. Don't do anything with the offset, just place the offset directly on 0. And this whole address, if you interpret it as a whole address, this just maps to what is the address that we have. Like this, now the position values will change. It's like 1, 2, 4, 8, 16, and 32. So the values are going to be 32 plus 16, 48 plus 250. The actual physical address that we got is 50. Now you can go and check if this makes sense here. So address 50 is going to fall 30, this is 32, this is 36, this is 40, this is 44, 48 is here, this is 52. So address 50 is going to come right here, right? The actual physical address 50, and we also found that the address that we are trying to access was just 10, so this is 0, 4, 8, 12, so 10 is right here in the second virtual page. Okay. And then the second virtual page was placed here, so we can diagrammatically see now the address translation that we just did makes sense. Okay. Any questions about this?
So there's nothing we can do about the size of the page tables?
Yeah, that's the focus of the next lecture. So that is definitely a big problem. Okay, size of the page tables is a big problem. And half of the next lecture we are just going to focus on how to decrease the size of the page tables. Any other questions? So just before we leave, just one more important thing I just forgot to say here is like, let's think about if a process is running. Okay, it is like the operating system is using its page table to do these translations, right? And when what to say? So internally, we may discuss about this in a lot more detail maybe in the next class. But internally, that is a single register in the hardware. Okay, hardware gives us a single register. It's called the page table base register. Okay, because the hardware needs to know where is the page table in the physical memory. Because address translation is done by the hardware. So since address translation is done by the hardware needs to know where the page tables actually reside in the physical memory. And so it has a register called page table base register. And whenever a process is running, that process's page table's base value will be loaded there. We may go into a lot more detail in the next class. And just like as before you leave, I would like to get like some sample feedback about, because there was we had 4 lectures and it's almost 25% of the course is done, 1/4 of the course is done today. So if you can just in a sheet, it's just open-ended feedback. In a sheet of paper, what are you feeling about the course till now? About the lectures, about the project, about the worksheet, whatever you may write. Okay. If you want a piece of paper or a pen, just let me know. I can hand it over to you. I have